Now recall our work from the previous section. We looked at how to find the volume of a revolution, or the volume of a solid, using the disk washer method. So let's do a little review. We started with a function. So we have this function y equals f of x. And we usually end up with functions that we can actually rewrite, So this function could be y equals f of x. And after solving for x, you might end up with x equals maybe some g of y. And we want to find the volume of the solid that we obtain if we take this region right here. Call this region, maybe I'm going to call it R for now. If we take R and we revolve R about the y-axis, so this is our y-axis. If we revolve y about the y-axis, what do we end up with? We end up with this solid right here. I'm going to call its volume V. So we end up with this solid right here. Let me get my highlighter. Yeah, this solid over here. Okay. Now with this solid now, to find the volume, the method we looked at was to get a little disc, like a little cross-sectional disc, or a cross-sectional washer. In this case, it's just a disc. Cross-sectional disc from the solid. So this disc, this is actually a fully solid disc. So let's just make sure it's solid. We get this disc and we find the area of the disc, and then we integrate throughout the whole solid. So if we run from the beginning of the solid to the end, in this case from the bottom to the top, like this, if we add up every possible disk in this solid, we're going to end up with the volume of the solid. And that's where integration comes into play, because the best way to add up such area is to integrate. So the volume is going to be the integral from a to b. A in this case is 0, but we're just going to write it as a to b of the area, which is pi, g of y squared, then dy. This was what we did. This was what we did in the previous section. And remember, I warned you to not use this as a formula, to develop the habit of always setting up the problem like we did. Look for the disk, sketch the problem, get the disk, and try to add up every possible disk using integration. All right, now we're going to modify this problem a little bit. Now, think about this. Oh, this is very little, too little. Let's see, maybe make this a little bigger. Now, how about let's modify the graph a bit. Just a little bit. So I'm gonna assume the same graph, but I'm gonna move it up and down in a different way, and you see what I mean. So I have this line, the axis. So I'm just gonna move it up. It won't be to scale, but I'm gonna just move it up like this. like this. Okay. Okay. And then I'm still trying to rotate about the y-axis like that. And I have this line here. Okay. So we have a line. Let's say this is some value of y, of x. So maybe this is x is equal to b. And maybe this is x is equal to a. But we know x is equal to 0 here, so don't even worry. Or you know what? Let's make it a little bit more general. So I moved it up. I'm gonna do something else to it. I'm gonna move it out a little bit. So I changed my mind. Okay. So we still want to rotate about the y-axis. You see what I'm trying to do? So let this line be x is equal to b. This is the line x is equal to b, where x is b. And this is another line, x is equal to a. Okay, this is not making sense to me now, or it's becoming what I want it to be. And we have our region. I'm going to call it R again. And we want to revolve this region about the y-axis. So let's go like that. And we get, oh no. No. Still no. Okay. Let's see what we have. All right. Sorry, it's not being identical. It's being a little bit different from what I had. But I think I'm being too much of a stickler. All right, I have that there. Oh no. And I have that. So after revolving, this is what we end up with. Something like this. All right, so that's what we end up with, a solid. Let's make it a true solid. Or I don't know if this makes it look more solid. I don't know. I think I just messed it up. You know what? It's a full solid. It's actually a hollow solid, right? This side, this part is hollow. Whoa, why in the world is it that thick? Make it like this. This side of the graph, this is all hollow, the highlighted region. So this is a solid. It's solid. And we're going to call it volume V. Now, we want to find its volume. Now, think about our usual approach. Let's try our usual approach, which is to get a slice. And I'm going to tell you what's wrong with that. If we try to get a slice, from here, cross-sectional slice, we get a disc. That's fine. We get a disc. But this disc is formed by the function. We're just gonna call this function x is equal to g of y. Well, let's not worry about it. Let's call it f is equal to f of x, or y is equal to f of x. Or yeah. So this part of the graph, or this green part, is formed by the function y is equal to f of x and the line x is equal to a. So remember that a, b, okay? So if we take this green, cross section to make our disc or washer to find the area, we'll be dealing with A, because it's going to be hollow. Ooh. So we'll be dealing with this disc. The outer radius is y equals f of x, or x is equal to g of y. And then the inner radius, so this is going to be, the outer radius is going to be, if we do it at a point y, take it at a point y, the outer radius is going to be this function right here. The function, I wish you could see. Yeah, this function, right? So it's going to be x is equal to g of y. That's the outer radius. Meanwhile, the inner radius is going to be a. Okay? That's the first disk. Okay? Now, how about if we go ahead and say, oh, I don't want to take my slice from there. I want to get a red slice from over here. In that case, this slice would look like this. Still gonna be a washer, kind of look like the first one, but something has changed. The outer radius is A or B. The inner radius is A. All right. Now, let's compare it to the previous problem. The previous problem, the radius is always g of y. Always g of y. Starts from 0, right? Maybe here, when x is 0, to the function itself. To the function. So it starts from here to the function. It doesn't matter where you are. If you pick it from here, if you take the slice from here, it ends at the function. If you take the slice around here, it starts from 0, where x is 0, to the function. So that your radius is always g of y. But in this case, if you try doing the disk or the washer method here, you might end up with two different disks depending on where you take your cross section. But for the method to work, the disks have to be the same. The formulation of the mathematical formulation of the area of the disk has to be the same. It doesn't matter where you take your cross section from. Now we have a cure for this. The cure is the shell method. Okay? The shell method is, instead of doing a disk, getting disks, we get shells out of our figure. So how do we do this? I'm going to show you. I'm going to try to redraw what I had drawn. Okay, so I'm going to draw it really quickly. Oh, no, that would be a mistake. I'm just going to take my time. Right. Right. Oh, no. Oh, no. Okay. Okay. What did I just do here? This doesn't make any sense. This doesn't make any sense. It's too long. Maybe not too long. Maybe I'm being too dramatic. Okay. Oh no, come on. Do me like that. Okay. So, still the same solid, hollow solid. It's hollow over here. It's open over there. All right. So now this is the solid. Okay. We're looking for the volume, mind you. We're going to call this volume V. Now, this shell method is actually very intuitive. Think about it, think of the solid as a toilet tissue. Sorry, a roll of toilet roll, right? So if you have a toilet roll and you start to open it, let's say this is your toilet roll. It's usually a hole in it, right? Okay. You can get a ply. Think of a ply as just being one revolution, okay? Having the circumference of the roll at the time. So you keep getting sheets out of the roll until everything ends. So now how about if you have the magical power to be able to go inside of the roll, and instead of getting from the outside, you just get a ply from inside, from somewhere inside. That's what we're going to do. We're going to get a red slice from an arbitrary point inside this solid. We're going to treat this solid as a toilet roll. So we're going to get a slice from here. It doesn't matter. Oh, from here. Let's do it from here. So this is A to B. So we look at this point, call this point X. That if we want to form a roll, then we have to get a symmetric point over here. So we end up with this roll. Okay. So this is the shell, right? So you're just getting a shell from somewhere in the solid. What you want to do is you want to open up this red shell. All right. Remember, the radius of this shell is a cylindrical shell. So it's a cylindrical shell. Remember, the radius is actually X. The radius of the shell is X. So if you open it up, you get a rectangle. The length of the rectangle is the circumference of the cylindrical shell. The circumference of the cylindrical shell is just the circumference of the circle, of this circle right here, right? Circumference of a circle is 2 pi r. The r in this case is x. So you get 2 pi x. So remember, this is just your cylindrical shell. This rectangle is just your cylindrical shell opened up. So its length is the circumference, and its height is just your function. And what is your function? Your function is y equals f of x. So its height is f of x. So what do we know? Its area, it's quite easy, is length 2 pi x times height f of x. So that our volume is just gonna be the integral from a to b of the area 2 pi x f of x dx. Now, I'm going to warn you again. Don't treat this as a formula. Treat it as a way of understanding a method. Whenever you get a problem, try to do this whole thing once again. Try to do it by yourself. Don't use this formula. It's gonna confuse you. I know what I'm saying. So let's do an example. So, an example or examples. All right. Okay. Let's say we're gonna let R be the region bounded by the graph of f of x equals sine x squared, the x-axis, and the vertical line x equals square root of pi over 2. Now, the question is to find the volume of the solid generated when R is revolved about the y-axis. Okay, now we're going to sketch our function and we're going to get our solid and everything is going to be good. So we have this. If you sketch the function y equals sine x squared, you end up with something that looks like this. So this is y equals sine x squared. And then we're going from 0 to x equals pi over 2. Square root of pi over 2. So this is the region that we're talking about. This is the region R. And we're going to rotate R about the y-axis. And if we do that, what do we end up with? No. Let's do this. We end up with something like this. A nice solid. Nice solid. Well done. Okay. So that's our solid. Now, this is our x-axis and that's our y-axis. Our vertical axis is in between. Okay, so what do we do? What we can do is we can think of getting a shell. If you get a red shell from here, think of getting a red shell, and you open up this red shell, open it up. If you got the shell at a point X, its circumference is going to be 2 pi x because its radius is x, and its height is just going to be sine x squared, so that its area is 2 pi x sine x squared. All right, so the volume of our solid, the volume here, is going to be the integral from 0 to square root of pi over 2, from 0 to square root of 0 to square root of pi over 2 of 2 pi x sine x squared dx. All right, this is a quite an easy integral to do. If you use substitution, if you let u be equal to x squared, so that du dx is equal to 2x, so that dx is equal to du over 2x. All right, so if you do that, this now becomes the integral from 0. I'm going to leave it as 0 to pi over 2. Well, if you change if you let u be x squared, then instead of square root of pi over 2, sorry, I need to make something clearer. I need to make something a little clear. This square root comes all the way down here, and it goes all the way down there, and it includes also the 2. All right, so our integral now will now just go from 0 to pi over 2, because we're squaring u is x squared. So when you square square root of x over 2, you get x over 2. So let's do 2 pi. We have our x, so this is sine u, and then the x is just du over 2x, So things are going to cancel out, this and that. 2 and 2 we cancel out, and then we are left with bring this here. We're left with the integral. You factor out pi, the integral from 0 to pi over 2 sine u du. If you do this correctly, you end up with pi. I think you end up with pi. Check it and tell me. All right. That's the final answer. Now let's try another problem really quickly. Again, let's get a region R. So let R be the region in the first quadrant bounded by the graph of y equals square root of x minus 2 and the line y equals 2. So we would like to find the volume using the shell method. Of the solid generated by when R is revolved about the x-axis. All right. Always sketch. And when you sketch, it helps. Even if you don't get the answer correctly, you end up getting some partial credit. So it's a win-win for you. You understand more when you sketch, and you get extra credit, or you get partial credit. So this is our y-axis. This is our x-axis. And the graph of y equals square root of x minus 2 is just the graph of y equals square root of x shifted to the right 2 units. So we have 1 unit, 2 unit, 2 units. We shift it like that. All right. And then we have the line y equals 2. So this is the line y equals 2. Okay. So that's y equals 2, and this is y equals square root of x minus 2. So this is our region R. That's our region R. Now, if we revolve this region about the x-axis, what do we end up with? Let's see what we get. We get we get 1, 2, like that. This, And then something similar here. And then we zip it and tag it by really making this like that and this. All right, so this is a solid. Let's get a red shell from this solid at this point, some arbitrary point y, right? So we'll get this red shell over here. So it's gonna be here like that, and then like that, like that. Okay, so that's our shell. So what do? We're gonna open up our shell. Open it up to get a long rectangle in this case. I'm not gonna draw it all the way along, but I'm just trying to stay with the configuration that the solid gave us. Okay, so this function is y equals square root of x minus 2. If you solve for x, so because this point is going to be x, right? The length here is going to be x. So x is, we can say that x is y squared plus 2, right? Y equals square root of x minus 2, or x is equal to y squared plus 2. If you solve for x, this is what you get. All right, so this length is y squared plus 2. Okay, now the radius over here, if you look at this, the radius is y. The radius is y. You're going from 0 to y. Y over here, and then y over here too. So since the radius is y, this length is the circumference of our shell. So the circumference in this case is 2 pi r, but r is y. So the area over here, the area of this little shell is, I'm not going to write it inside there. Let me write it outside. Area is 2 pi y times y squared plus 2. You see that? So let's come back to our solid. We're looking for the volume. The volume, V, is now going to be the integral. Now, where are we going from? We're going to be running along the y-axis because we've written everything in terms of y now. And because the shell can be expressed well in terms of y. So we're running from 0 to 2. Y equals 0 to y equals 2. So we go from 0 to 2 of the area, which is 2 pi y times y squared plus 2, and then dy. And you can solve this all day, every day. And if you solve it using substitution, think of your substitution to be, I think if you do u equals y squared plus 2, you get it easily. Actually, you don't even need substitution. You can just open it up. So you can just do the 0 to 2. I'll factor out the 2 pi. 2 pi is a constant, and constants are pushovers. You can factor them out. So this is y cubed plus 2y dy. So if you do this integration, I think you end up with, I got 16 pi. I want you to check my answer. Okay, so that is example 2. Let's try another example. Now, I have a third example. Number 3. We're going to let R be the region between the curves y equals x and y equals x squared. All right. So well, there are two parts. A, find the volume of this solid obtained by rotating R about the y-axis. And I want you to use the shell method. This is actually a simpler example, but I want you to pay attention because I'm going to make you do something else. All right, so we have y-axis, x-axis. So R is a region bounded by y equals x and y equals x squared. So let's call this region, this is R, I'm going to call it green region. So this is y equals x, this is y equals x squared. Right. So you're going from, if the point of intersection here is definitely 1, if you want to get it solved, you want to set x squared equals to x, you get 1. So you're revolving about the y-axis. That's what you're revolving. So after revolving, what do you end up with? You end up with that it's a little bigger, but it's fine. It's fine. So you get this solid. So you already see something here, but maybe you don't see something else. Maybe you see what I see or what I'm gonna do. But you are supposed to see something else. I'm gonna come back to that. But what I'm gonna do now is I'm gonna use the shell method. I'll get my shell at a point x. This is the height of my shell, cylindrical shell, and that is the circumference of the shell. Open up this cylindrical shell. I am going to cut it off. Cut it. Cut it off. Bring it here. All right. The circumference, its radius is x, so its circumference is 2 pi x. 2 pi x. Its height is the difference between the two functions. The top function is x, the bottom function is x squared. So it's going to be x minus x squared. So that this area here, the area of this little rectangle is 2 pi x times x minus x squared. That's it. So we're looking for the volume of this solid. So the volume, again, is just going to be the integral. You're going to go from 0 to 1 because you're integrating all the shells from 0 to 1, every possible shell. This red shell, maybe another green shell, a green shell, get another shell. So all the shells, you're running every possible shell from 0 to 1. From 0 to 1, every possible shell. If you get every possible shell, the area of every possible shell, I'm saying area because the shells are very thin, so we can just think of the volume as the area. So think of the area of every possible shell and then integrate it. If you do all that from 0 to 1, you're going to cover the whole volume. All right, so we're going from 0 to 1, and we have 2 pi x minus x squared dx. So again, if you expand this is quite easy. Factor out the 2 pi because constants are like little bunnies. You can do anything to them, nobody cares. Bring them out. So you have x squared minus x cubed dx. All right, if you do this well, you get the answer pi over 6. Now, this is the shell method. Now I want you to try this. Try the same problem using the washer method. Washer method. Think of the washer method. What do you do? Instead of a shell, instead of the red shell, you're going to get a disc. So what color should I make my disc? Let's make it like a bright green, or maybe orange. Oh, you know what? Bright green, very, very bright green that looks like yellow. Okay, so we're gonna get a shell, do the shell, or do the washer over here, and then there. Okay, I just messed up everything, but it's fine. So you're gonna end up with this, a disc like that. And the disc is gonna also still run from, it's gonna run along the y-axis, it's gonna run from 0 to 1 still. Find the inner radius and the outer radius, and then integrate it. So that's what I want you to try using the washer method. Okay, so I think I am going to stop here for now, and we can do more stuff in class. This is a long video, but oh well.